In this problem, our goal is to find the lowest common ancestor, or LCA, of two given nodes in a binary tree. The LCA of two nodes P and Q is the lowest node in the tree that has both P and Q as descendants, with a node allowed to be a descendant of itself. To solve this, we use a recursive approach to traverse the binary tree and identify the LCA. Here is a simplified explanation of the algorithm. The function lowest common ancestor takes three parameters: the root of the binary tree and the two nodes P and Q for which we need to find the LCA. It returns a pointer to the node that represents the LCA. The first step is to check if the current node root is null or if it matches either of the nodes P or Q. If any of these conditions are met, we return the current node. This is our base case for the recursion. If we reach the end of a branch or find one of the target nodes, we return that node because it could potentially be the LCA or lead us to the LCA. Next, we search for the nodes P and Q in the left and right subtrees of the current node by making recursive calls to the lowest common ancestor function for the left and right children of the current node. Once we have the results of these recursive searches, we determine if the current node is the LCA. If both the left and right subtrees return non-null values, it means both P and Q are found in different subtrees of the current node. Hence, the current node is their lowest common ancestor and we return it. If only one of the subtrees returns a non-null value, it means both P and Q are located in that subtree. Therefore, we return the non-null subtree as it contains the LCA. By following this recursive approach, the algorithm efficiently traverses the tree and identifies the LCA. The recursion ensures that we explore all possible paths in the tree, and the conditions we check guarantee that we correctly identify the lowest common ancestor. This algorithm's effectiveness lies in its ability to utilize the hierarchical nature of binary trees. Each recursive call effectively narrows down the search area by focusing on a smaller subtree. This approach aligns with the divide-and-conquer strategy, where the problem is broken down into smaller, more manageable components. As a result, the algorithm can quickly eliminate large portions of the tree that do not contain the nodes of interest, thus enhancing efficiency. In summary, our solution involves recursively traversing the binary tree to find the lowest common ancestor of two given nodes. By checking each node and its subtrees, we can determine the node that serves as the lowest common ancestor, ensuring a correct and efficient solution to the problem. This recursive approach, combined with the structural properties of binary trees, allows for an elegant and effective solution to finding the LCA in a binary tree. Now, let's test this algorithm to make sure it works. Remember, there are many ways to implement an algorithm, and trying out different ideas is always a good practice.